Hi, my name is Ahmed, and I'm going to talk today about radiation damage in nuclear fuel clad due to fission heavy ions. Well, I'm going to be talking specifically about irradiation-induced hardening, and only that due to xenon 140. The poor performance of zirconium-based cladding in accident conditions have raised concern about its safety, and have stimulated efforts to develop a more accident-tolerant fuels. There are many important aspects to be considered when looking for alternatives to current clad materials. However, we are only concerned here about irradiation-induced hardening. Almost every time an ion makes a collision with a target atom, the atom is knocked out of its lattice, forming what is known as a primary knock-on atom, and one vacancy is left behind. This primary knock-on atom gains energy and starts having its own collisions, leading to the production of more recoils, known as secondary knock-on atoms. For each collision, 2-point defects are formed. First, the atoms knocked out of their lattice sites form interstitial atoms. At the same time, vacancies are produced because the recoil atoms leave behind empty lattice sites. Some of these vacancies might be later filled with atoms, making the number of vacancies slightly smaller than displacements. These defects restrict the motion of native atoms, increasing the hardness of the material. Therefore, for a material to have a good performance under ion irradiation, it needs to have low number of defects produced per ion or have the defects restricted near the surface. To evaluate irradiation hardening of a material, we need to estimate defect production on it. And this can be done using the transport of ions in matter software, also known as TRIM. One good alternative to zirconium-based alloys is the austenitic stainless steels. Comparison between the properties of zirconium and stainless steel shows that stainless steel have better mechanical characteristics. This indicates that stainless steel might have better performance under irradiation by heavy ions. Our goal will be to estimate defect production in zircaloy 4 and austenitic stainless steel 348 to predict which of them will have less radiation hardening. The target materials were built on trim using the atomic percents of atoms composing each of the two materials. It is expected that austenitic steels will show better performance under irradiation by heavy ions than zircaloy 4. Since available data indicate that stainless steel has better mechanical properties and generally perform better under irradiation. Due to the lack of time, only one ion was chosen to perform this experiment, xenon 140. The ion is one of the most probable fission products. It is estimated to be emitted with energies ranging between 40 and 80 MeV. We are going to simulate an ion emitted inside a fuel billet, directly towards the clad. However, we are only interested in ions that penetrate through the fuel to the clad. Therefore, we are going to only consider ions emitted in the last 2 microns of the fuel. The final setup should look as follows. Ions will be randomly emitted anywhere on the first layer of the target, which is 2 micrometers of uranium dioxide. Then it will go through a second layer of 80 micrometers of helium gas before finally hitting a 10 micrometer layer of clad material. The trim option calculation with full damage cascades was used to simulate 2500 ions, and the following results were obtained. First, the green curves describing the ion distribution show that ions penetrate deeper into zircaloy than stainless steel. The projected range in zircaloy was found to be 5 micrometers, as compared to 3.7 micrometers in stainless steel. As a result, the distribution of interstitial atoms given by the blue curves shows that target recoil atoms are more deeply distributed inside zircaloy than in stainless steel. The area under the blue curves is the number of interstitial atoms per ion, which is almost equal to the number of displacements per ion. This was found to be 120 K displacement per ion on average in the zircaloy 4, compared to 123 K displacement per ion in the stainless steel target. Also, the distribution of vacancies show agreement with the distribution shown above. The number of vacancies is slightly higher for stainless steel than zircaloy, but the vacancies are more deeply spread inside zircaloy. Another interesting observation is the transport of some helium atoms from the gap into the clad, but the number of these atoms are very small and they are only confined to 0.16 microns of the clad surface, so we need not to worry about them. Also, some of the clad atoms are removed by the recoil atoms that come back out of the clad. This is known as sputtering. However, less than 1 atom was found to sputter per ion, which is not significant. Although the number of defects per ion is slightly higher for austenitic stainless steel 348 than zircaloy 4, the penetration depths of ions, recoils, and vacancies was found higher in zircaloy 4. This allows us to conclude that austenitic stainless steel 348 has less radiation hardening overall than zircaloy 4. Thank you for listening and have a good day.